Well, today I decided to make an assembly program. That's right, I decided that I want to torture myself with the lowest of the low end languages. So, specifically, I'm planning to use x86-64 assembly because I heard it's one of the more challenging versions. But it's not like I'm going to be making RCD out of scratch like Chris Sawyer. I was thinking of something simple like adding 5 to your current age. Okay, the first thing that we need to know about in terms of assembly is that assembly uses registers. Assembly doesn't deal with fancy stuff like variables named fluffy bunny count. Nope, it wants everything to go directly into a register. Do you want to add two numbers? Shove one in register A and one in register B, and then tell the CPU, hey, put these two together, and then take the result and put in register C. It's like talking to a caveman accountant. It's efficient, but only if you can grunt correctly. So in terms of registers, you might see me use RDI, RAX, RBX, RSI. So anything starting with R is most likely going to be a register that is 64-bit, while the 32-bit stuff starts with E, like EAX, EBX, ECX, and EDX. Uh, I'm probably not going to be using any of the 8-bit or 16-bit registers as well, just because, I feel like working with 64-bit makes life a little bit more simpler. Enough yapping, let's get to the actual coding. Writing an assembly program is like making a sandwich from absolute scratch. First, you have to write the code. That's like laying out your ingredients on the counter. Our second step is to assemble it. Now you're going to be stacking the bread, meat, cheese, and whatever questionable choices you made. Next, you have to link it. This is you smushing the sandwich together so it doesn't fall apart when you pick it up. And our final step is to run the executable. And that's you taking a bite. And yeah, I couldn't find a better analogy for this. Well, let's get to the actual programming. And yeah, everything was improv. So, I start by importing printf and scanf from the C standard library because they let me handle input and output without reinventing the wheel. So, printf is just going to output something and scanf takes in an input. And you make comments in this type of assembly with semicolons, which I found really interesting. Now, global main, all that does is just tells the linker this is a starting point of my program, just like main in C languages. Now, section.txt is where you put your actual code. These are instructions, from here, CPU will actually execute stuff. So, and main is a label, right? And it's just going to be our label to start in our specific case. So before I actually write assembly code, what I like to do is write out my entire program in C. This is to visualize what it would actually look like, right? Before I get to the assembly. So what my program would do first is it would print out enter your age, right? And from there, it's going to take in an input, right? And firstly, when it's outputting, it's going to use printf, and when it's going to be taking an input, it's going to be using scanf, right? And when we're using scanf, it's going to be taking in age, right? And then we're actually going to increment the value of age by a value of 5. So age plus is equal to 5. And then we should finally give a response to the user, which is going to be in 5 years, you will be the age plus 5 equal years old. So that's what it would look like in C. And of course, I made a syntax error and forgot my semicolons. All right, let's fix that and move on to the next section. So here in the section.data, and it's not to be confused with anything else, but it's just going to be where we dump our variable string and other stuff. It's really important though, because here we're going to have the prompt, right? Enter your age, it's going to store that string, right? And when we say age prompt db, db means defined byte. This just means we're putting characters into memory 1 byte at a time, and the 0 at the end is just a null terminator, which is just, just like in C. but we don't use 0 in C, but we're just having an null terminator. Now, format prompt DB. This is just the format string for scanf. It tells scanf to expect an integer, right? And we're also terminating this one. And yeah, let's move on to the next one, which is age. Age DQ. DQ means define quad word, and we're basically allocating 8 bytes for the age, for the user's age, actually, I should say better. And yeah, that's all this basically means. And the response format is our final string that we need. It's just stating in 5 years you will be percentage d years old. And actually, this is something new. We have 0AH, 0DH, 0. It just means new line and a null terminator. That's what that means. So yeah, hopefully this makes sense. So as we continue to program in assembly, we are bound to see these guys over here, and they're called opcodes. Now, this list is just a small list of opcodes. There are plenty more. Now, what do these opcodes do, and what do they stand for? Now, opcode actually stands for operation code, right? And what they do is fairly simple. They basically tell what we should do with our registers, right? For example, move. It moves, right, data from one place to another, right? So it doesn't destroy the source, but rather it just copies it, right? Now, the next one on this list is call. And what call does is it pushes the address of the next instruction onto the stack and jumps to the address of the function, right? Now, it was a little complicated way of saying that it can kind of help us to summon functions. And now let's look at pop. What pop kind of is it takes off the top value of the stack into a register, right? It pulls the top value off the stack into a register, right? And now CMP, which stands for compare, it just compares two values or two registers, right? And JMP is just jump, right? We can use this for jumping from one part to the next, especially when we use it with compare, right? So you usually see jump and compare together. It's kind of like go to in C. Now we are going to be using opcodes in conjunction with registers to turn each of our lines of C code into assembly. So we're going to start with our print statement. Now our print statement is going to output to the user, enter your age. So we're going to be using the move opcode to move my age prompt into the RDI register. So we can see the first line is going to be MOV RDI age prompt. So we're going to be moving age prompt into the RDI register. Then we can see that our next line states MOV RAX, 0. This just means that we're going to be moving 0 into the RAX register. Now this is required before calling a function like printf to indicate that there are no floating point arguments being passed in. When we call a function like printf, the computer expects the stack to be lined up in a special way. It must be 16 bytes aligned. To make sure this happens, we push RBX onto the stack before the call and pop it afterward to keep everything balanced. So this is what is happening when we're doing push RBX, call printf, and then pop RBX. This is kind of a pattern that you're going to see when we're going to be calling functions. Okay, so now we're at the part of our program where we're going to be taking the actual input from the user. So to do this, we're going to be using scanf. And in assembly, we're going to start by using the MOV opcode to load the address of the format string, right, that we created before, and we called it format prompt, into the RDI register. This is the first argument to scanf. Now, scanf actually needs a second argument, and this is the address where the input is actually going to be stored. So remember, we created an age variable. So we're going to move the address of the age variable into the RSI register. RSI is actually second argument in the calling convention. So after RDI becomes RSI, so on and so forth, as we create new registers. And as usual, we're going to move 0 into the RAX register to indicate that there are no floating point arguments being passed. And finally, as we did before, we align the stack before calling scanf by pushing RBX and restoring it afterward by popping RBX. Okay, to now add 5 to the age that we inputted, we have to move the value stored at the address of age into a register like RSI. And to do that, we're going to use square brackets. So we're going to put square brackets around age, which is just to say it means the value at the address of age, right? We don't want memory, we want the actual value. And we want to add 5 to that value using the add opcode, right? As we do here, we do add RSI, comma 5. The final function call that we have to make will be for a print statement that will output the updated age using our response format. This will use the same idea as our previous print statement, where this time we were going to be using the MOV opcode to move response format that we created into the RDI register. Then, as usual, we have to move 0 into the REX register to indicate that there are no floating point arguments being passed in. Then, when we call a function like printf, like before, we have to make sure that our stack is aligned. So we push RBX onto the stack before we call printf and pop it afterward to make sure everything is well and aligned. Now to make a smooth exit, we move 0 into REX and type RET, which is similar to return 0 in regards to C syntax. Okay, so now let's assemble our ager.asm file into a 64-bit Linux object file called ager.o and get it ready to be linked. So the first step is to write down NASM. Now, NASM actually calls NASM.
Do me a favor, please. Get out of here. Get out of here, man. Shit, I'm saying.
Which is a net-wide assembler to compile our assembly code, and that's what we're going to be using. And then we write down -f elf64, and this actually specifies the output format. elf64 means you're assembling for a 64-bit Linux system using the elf format. Now, ager.asm, this is our input file, right? This is the assembly source code that we wrote. -o ager.o basically tells NASM to output the file ager.o. This is just an object file and not our final executable. So for our last command, we're going to start with the GCC, which just basically means we're going to be using the GNU-C compiler, and we're going to be using it as a linker to create our executable. -no-pi basically disables position independent executable mode. I know it's a lot of words. What this basically does is it allows our operating system to load your program at a random memory address. This is very good for security, right? What I'm doing right now is not best in terms of security, but I'm just going to disable it because, frick security. But you should do it. Add.o basically is our input file, right? This is the object file we created with NASM earlier, and -o add just tells the GCC to output our executable. And finally, we can run it, and you can see that we can input an age of 5, and there we go. It works. We're getting 10. So that's it for this video. Thank you so much for watching. Hope it was informational.